to Bitcoin Podcast. The only one that's making your money is you. Listen to the Bitcoin Podcast. So hold on and listen to the Bitcoin Podcast.
Hell yeah.
Welcome to the live stream about teaching ourselves some cryptography on the weekend, on a Saturday in the afternoon.
What are you guys doing on your Saturday? Come join us. Learn some cryptography. Learn some maths, as the Europeans say.
For those who are new, we're streaming to multiple platforms at the same time. We accidentally recorded the first episode instead of going live. So this is the second episode. In the first one, we went over essentially the book that we are going through, which is called ZKDL Lecture Notes from Distributed Lab, a Ukrainian group that does applied cryptography for various different projects in the Web3 or crypto industry. Right now, we are, I don't know if I'm on the right page that we're on, because I don't remember where
I'm on. It's no, the page that I'm on is 14. It starts
14.
with mathematics crash course.
Okay.
That's where we left off last time.
All right, cool. So what we've been doing is trying to pre-read a little bit during the week, so that when we record on Saturdays, we're not looking at the content with entirely fresh eyes. That helps us kind of parse things a little bit faster and helps us have conversations about the actual content versus just getting stuck on things. So with that said, I don't know if you want to kick it off and read the first part, Corey.
Yeah, I'll do that. Let's see. As any cryptography subfield, cryptography requires a solid knowledge of mathematics. While the practical development of cryptographic protocols might not include the need to understand the whole underlying theory, much of it typically still arises. For example, one might need to implement the elliptic curve pairing operation verification in a zero-knowledge proof system, or RSA encryption and decryption methods in circom circuits. In case you specifically develop a zero-knowledge system from scratch, there is no need to explain why you need to understand the underlying theory. This part of the book is dedicated to the mathematical background required for cryptography. Namely, we will cover essentials specified in Table 1. So Section 3 will handle number theory, which is modular arithmetic, ring, Z-space in field Z, and I don't know how to say that, Fermat's little theorem. I don't know what that is. 4, abstract algebra, groups, subgroups, fields, prime fields, FP, isomorphisms, automorphisms. I'm aware / comfortable with most of that. 5, polynomials, quite comfortable with those. Divisibility, Lagrange interpolation, and Schwartz-Zippel lemma. I don't know that one.
I don't know that one either.
6, linear algebra basics. This is a strong suit of mine. Basic operations over vectors and matrices. 7, field extensions, definitions of FP of M, FP to the M, F of P to the M, field multiplicative subgroup, and algebraic closure. So we're all going to learn that. Not today. Probably going to go through like 10 pages, I imagine, today, right? We'll figure it out. That's our goal. Yep. 10 pages an episode where we yell at each other about what's wrong and what's right. So this is not a mathematics book, so we will not prove every mentioned theorem or lemma, but we do provide reasoning for some key facts. We focus on the practical side of the theory, providing examples and exercises for the reader to solve. Moreover, the solutions to the exercises can be found in part 5 for the reader to check their understanding. That's interesting. We should try that.
Yeah, I did that already.
Okay, great. Awesome. The reader should already be familiar with the very basics of the first 4 topics, so they will be covered for the sake of completeness in reminding the readers of the key concepts. The last topic, field extensions, is less frequent in the mathematics curriculum, so we will cover it in more detail. In case you feel comfortable with the aforementioned topics, feel free to skip them and move to the next part of the book. Finally, if you are unsure about your knowledge, you should open the corresponding section and check whether you can solve exercises in the end without any help. I am not comfortable solving probably any of those except for the linear algebra part. And most of the polynomial thing, I bet. Let's see how it goes.
Okay, I'll read the next part. So, introduction to number theory. As you can recall from high school math, typically real-world processes are described using real numbers denoted by, how do I say this? Just
R space. Real space.
R space, real space. Okay.
I mean, R is
You
real,
don't
so like
say
the real space.
calligraphic R, or not calligraphic, but like I don't know, like double
I'll
line
chat
R.
GPT it. I'll Claude it.
Okay.
Ask him how you're supposed to
Okay.
say that while you're talking.
I'll say real space R because that makes sense to me. But for example, to describe the position or the velocity of an object, you would rather use real numbers instead of fields, groups, or p-adic numbers. However, when it comes to working with computers, real numbers become very inconvenient to work with. The primary reason is that the set R is uncountably infinite, so the computer can only store the approximation of a real number, as the precise interpretation of the real number would require the infinite number of bits. For example, different programming languages might output different values for quite a straightforward operation, such as an addition 2.00001 plus 2.00000. This becomes a huge problem when dealing with cryptography, which must check precisely whether two quantities are equal. This is why the cryptography must work with integer-based formats. One of the earliest and most fundamental branches of mathematics is number theory, which deals with the properties of the integer set Z. Although, as we will see later, we will primarily need notions of finite fields and groups further, the basic concepts of number theory will be used extensively nonetheless. So just a little bit of context in case people who are listening aren't people who program. This is actually a really huge thing in terms of having enough bits to represent like a floating point number. So if you think about like most modern systems now, everything is like 64 bits. And I don't know if we should go into like what bits are just for people
It's like
who don't
floating
know,
point precision.
yeah, so like just for people who don't know anything about computers, who are just like listening because they see people talking about something that looks like Google de Gook.
Yeah.
Bits are 0 and 1. Like your computer is basically parsing everything in terms of zeros and ones at the end of the day. There's a number of optimizations that are done by your computer processor that take programming languages that are like let's say business logic written in various different programming languages, whether they're more human readable, which are generally the higher level programming languages, to the lower level, more machine code looking business logic that gets encoded. So like in the old days, when the computers were not so smart, they had to write in low level programming languages where it doesn't read like a book. It reads more like a bunch of commands in a bunch of places where you store things. So what I mean by that, you have a lot of go-to labels, jump statements, registers that you're throwing values in. And these
The languages
registers,
actually emulated punch cards in a lot of ways.
I never played with punch cards. Did you?
No, but I programmed in Fortran 77, so like
Okay.
and my parents taught me a lot about them. I've seen them and held them and played with them, but not like actually put them into machines. That was my parents' job.
My dad said he ran a computer lab in college. He was a chemistry major in the Philippines back then, and he used punch cards. And
my parents both were computer scientists that were like punch card people.
Interesting. That's cool. Okay, so yeah, that's why we need integers. Whenever we're doing cryptography, computers they like integers, especially when you're gonna do like as I'll do a little bit of foreshadowing here, but we're going to have to do a lot of modulus operations on integers, essentially, because what we need really big numbers that are impossible to calculate, especially in cryptography, when the goal is to encrypt something in such a way that a computer cannot reverse the encryption. You're trying to hide in plain sight. And to do that, you need really big numbers that can be turned into small numbers for computers to, I guess, verify things are being done correctly. That's kind of like the most high level explanation I can give. Maybe it makes sense to you, maybe it doesn't. But if it doesn't, just ask for clarification.
Something that was interesting to me, like something I ran into was with like the concept of machine precision. And so like depending upon the bit size of your number, you then have a certain precision on what the difference is between any given number. And if you do a lot of algorithms that are iterative, meaning they have multiple steps in order to get to the end solution, and you need accuracy that is really, really, really high, you need to care about how machine precision adds up for every given calculation of the iteration. Otherwise, you end up with something that's so far off base because you're rounding at machine precision, and then that error accumulates over and over and over and over, and then grows to be larger than the discrepancy that you need it to be once you get to the final answer. So like certain weird things that come into play when you're doing with computers trying to represent numbers.
Yeah, because all the business logic essentially turns into math at the gate, logic gate and transistor level. So like if you have math that doesn't make sense, your output of your computer program that you're trying to run is not going to make any sense. And so like
this just gets into like
buffer overflow.
Even the representation of the math, right? And so like your math can make sense, but if you don't represent it well in the code, and care about some of the things on how like the math turns into like opcodes, then you can end up with the wrong number even though your math's good.
There's so many different, and then back in the day when error correction in computers was worse, like you want deterministic output from a processor. And this goes beyond my depth because I'm not somebody who makes computer processors, but computer processors are expected to be deterministic in output by everybody, but they actually don't operate deterministically under the hood. And I don't know how that works because that's beyond me again. It's for the big brains at Intel and AMD who make the chips.
And look at that. Gotta hash it out.
Okay. You want to read the next section? This one? Division?
Me too?
Yep, go for it.
Let me put this back in. Trying to play with the vertical stuff. The people who are watching vertically on like X and Instagram aren't going to be able to see the text based on what we're showing here, but it's fine.
Oh, should I can full screen. I can go like this. I can remove my notes. Let me see.
Yeah, just do that, I guess.
Just try and... No, hold on.
Let's see. Division, GCD, LCM. We start with the most basic definition of number theory, divisibility. So definition 3.1, integer A is divisible by a non-zero integer B, denoted B bar A, or B is a divisor of A. If and only if there exists an integer K that exists within the integer numbers, or the numbers, such that A equals K times B. Let's see. Okay, that makes sense. Example 3, let's consider the following example. 41 bar 123, since 123 is equal to 3 times 41. And then 2, was that not bar? Like
so you just read it
5
as
is not a divisor.
41 is a divisor of 123.
5 is not a divisor of 29, since there's no integer K such that 29 is equal to K times 5. That makes sense? I'd never seen the shorthand for that, though.
Yeah, me neither. I didn't know that.
Let us now explore some more basic properties of divisibility. So lemma. So given that definition, a lemma is 3.2 divisibility properties for all ABC that exist within the numbers or the integers. See, 1 is divisible by A. Any number is divisible by 1. Oh, is a divisor of. 1 is a divisor of A. For any number. Let's say A is not equal to, if A is not equal to 0, then A is a divisor of A. Obvious, A can divide itself. A is not equal to 0, then A is a divisor of 0. And B is a divisor of A, and C divisor of B, then C a divisor of A, formula called transitivity. So, okay, so divisibility is transitive. That's the property you get. 5, B is a divisor of A, and B times C a divisor of A. What's the back and forth symbol there? I forget.
Which one?
Number 5. What is that? Double arrow.
So
forgot to say that.
It's the same thing basically. That's how I read it. It's the same thing. Okay. Or like can be rewritten as.
What is the property there? It didn't list it, but I get it. Basically, you can do the same thing with a constant.
Yeah, I think it's also like transitivity.
Multiply a constant, right? And transitivity. Yeah, it looks like transitivity. If C is a divisor of A and C is a divisor of B, then C is a divisor of A times A plus or minus B times B, or alpha times A plus or minus beta times B for any alpha beta that exists within the integers.
Yeah, I can look up what's this called because it looks like transitivity.
That's
Here, let me.
fine. Okay, I get that. Basically, 6 follows from 5, it looks like. But it's also transitive. So like 6 is a property of 4 plus 5. It looks like in my head, intuitively speaking. Anyway, we can keep going. This way, we have A and B, with B as a divisor of A. We can safely divide A by B. However, in the majority of cases, it so happens that A is not divisible by B, making it hard to define the division of such cases. For that reason, consider one of the central theorems of number theory, the division theorem. Theorem 3.3, the division theorem, says for any integers A and B that exist within the numbers, there exist unique integers Q and R that also exist in the numbers with 0 less than or equal to R less than or equal to B. So R within the boundary of 0 and absolute value of B, such that A is equal to B times Q plus R. So that means basically like you get a remainder.
So
There's
the one
there's a number of divisors. Like there's a multiplicative you can add that will then give you a number that's smaller than the original number plus some remainder. This is basically the remainder theorem, if you will. This gives us 2 more operations which are useful. The floor operation, which is A/B, or those symbols, whatever. A divided by B is defined as Q. This operation is a standard dividing operation. Look at a spelling error there. Commonly used in programming languages. You can make a PR to the programming or to the source code.
I already did.
Oh.
Yeah, I
mod
fixed it
operations. A mod B is defined as R. So this operation is a standard mod operation commonly used in programming. So that's the mod operation. I think is where you're going to spend a lot of time in, especially in cryptography, because you're always used integer fields.
Yep. I'm trying to fix it actively as you're reading.
I can do mine.
It doesn't look like that on the tablet.
I can do mine.
Yeah, if you want to do yours. Yeah.
So we'll just blow this up so that it's central.
Right, zoom in. Yeah, nice.
Remark. There is one caveat with programming languages, though. Oftentimes, the quotient Q and remainder R obey the aforementioned condition A equals B times Q plus R, but with the difference that the absolute value of R is less than the absolute value of B, allowing 2 possible values for R, including negative. Okay. So an example of that, we know that 5 is not a divisor of 29. However, definitely we can express 29 as 5 times 5 plus 4. So 5 squared plus 4. Similarly, it is evident that 34 is not a divisor of 123, but 3 times 34 plus 21. Okay. Compare the results. So you have some code here. Let's look at this.
I just ran this in a WSL instance.
A what?
Yeah.
WSL instance? What's that?
Yeah. Because I'm on Windows, right? So I just popped open VS Code on the computer that the tablet is streaming to, and then I ran this.
Yeah.
Just to, because they're not this one, but there's another one where actually I didn't know. There's a way of a succinct way that's Pythonic that I didn't know before, and I had to look that up. Not in this one, but the next example.
I don't have IPython. What the fuck?
Might be actually good to show.
Yeah. I'm installing a few things.
Okay. I don't know if I can spin it up real fast.
All right, I got IPython going. Let's see. I'll just change my screen over to it.
Okay.
Stop screening. Window. Share. Let's see. How's that? Well, I just killed it. That's neat. For some reason, this does not like to be maximized on the screen.
I wonder if I could just grab this. Nope, cannot. Interesting.
There we go. Let's try this now. Add a stage. So let's pull the code. I don't know if it'll copy and paste from a PDF very well. Let's find out. I don't like the indentions. I think I need to. Yeah. Five, 4. So it worked. So A divided by B gives 5. No remainder. So yeah, so Q is just going to be how many, what is the divisor of A into B? R gives you the remainder. So A mod B. And so there you go.
Interesting. There's another error. Tuple is not supposed to be capitalized.
Huh? I got mine. Are you doing on yours?
Yep.
I copy and paste nicely. So I did do the intentions of the definition.
I wonder if I'm running on a different. No, I'm on 3.10.12. I don't know. I didn't like capital T and tuple for the output.
I'm 3.14.
Hmm.
Anyway, moving on. We'll use yours. We'll have to get used to the what's it called? Start using the scenes here, so we can like have scenes for various types of things we're going to show.
Mm-hmm.
That could be useful.
Yeah. I haven't used it. I assume it's like Streamlabs.
Yeah, you just set it up. It'll. All right, so we got that going. Division operations. It is common to check for any shared factors between the two numbers. This is where concept of greatest common divisor, or GCD is short, comes into play. Greatest common divisor, GCD of A and B, is defined as the integer D that exists within the natural numbers such that D is a divisor of A and D is a divisor of B. D is a maximal integer that satisfies the first condition. One might write the above definition. That's okay. That's the incorrect way of saying right. Wrong, right? One might write the above definition more concisely as GCD of A and B equals the max of D existing within N, parameterized by D, D a divisor of A and D a divisor of B. Okay. So there could be multiple divisors of both, but you take the max as the greatest common denominator. There's an example, few pairs, integers, GCD 14. That makes sense.
Oh, whoa. It went way further.
Well,
That's crazy.
I'm reading off of
There's
mine.
some sort of. Okay, good.
There you go.
Okay.
So GCD to 1, that means it doesn't have a common divisor other than 1. It's trivial. 2. Definition 3.5. Integers A and B that exist within the integers are called coprime if GCD of A and B is 1. So 3 and 4 are coprime in the above example.
Mm-hmm.
Let's see. As with any fundamental concept, let's explore some basic properties of the GCD operation. So given that we have greatest common denominator, let's see. The greatest common denominator of A and B is equal to
greatest
B
common
and-
divisor.
It's the same thing.
No, it's not.
Greatest common denominator and greatest common divisor.
Oh, yeah. Sorry, it is. Yeah.
B is the same as
Dividend.
B.
Yeah.
Okay. I don't understand 1. What is it? Greatest common denominator divisor of A and B is equal to B interchangeable with? Is that what that means? Like B is a divisor of A.
So if I guess, yeah, you just read it like you just said it. So if the greatest common denominator of A and B is B, then B is a divisor of A. Yeah. Like basically B will go into A.
Okay.
Yeah. These are like things that we take for granted.
Oh, okay.
Blown out math.
I get it.
That's
That makes sense to me. I was just reading it.
Yeah.
Strangely.
Yeah.
Okay. If A is not equal to 0, then greatest common denominator of A and 0 is equal to A. That makes sense.
Mm-hmm.
There exists a delta within the natural numbers such that delta is a divisor of A and delta is a divisor of B. Then delta is as the divisor of the greatest common denominator of A and B. Okay. If C is greater than 0, then the greatest common denominator of A and C and B and C is equal to C times the greatest. That makes sense. It's just this transitive. I think it's transitive. It's like transitivity.
It looks like it, but I'm not going to call
Keeps
everything
going into
transitivity.
Yeah.
Because sometimes like more formal math, like the other one was called cancellation law or cancellative property, which I didn't even know that was a phrase. So I'm not
When you get into like matrix algebra, then
by
becomes
saying, yeah. Well, what I mean is, I'm like, it looks like transitivity, but I'm not going to be like, yeah, transitivity everywhere.
yeah,
Like,
that's fine. Yeah, that's
the
true.
math dude is going to like get in our comments and be like,
Oh, good. Yeah, math people. If you say something wrong, don't be a bitch. Say something.
Yes, please.
Let's see. Now, from the programming standpoint, you might ask how to implement the greatest common denominator computation in practice. Consider the following lemma, which, as of now, might seem quite abstract. For any integers A and B exist within the numbers, we have greatest common denominator A and B equal to the greatest common denominator of B, A minus B.
This is interesting, actually. This implementation is interesting because I didn't know. I'll read this one. So after Corey read the lemma 3.7, so it says, how does this help, or how does it help? Here's how. Instead of computing GCD of A and B directly, we reduce the problem to a simpler one, where one of the numbers is smaller. We apply this recursively until at some point one of the integers is 0. The other one will be the GCD result as follows from the second property of definition 3.6. Surprisingly, this can be written in a couple lines of code. And so the question that I had here was like, I'd never seen this format of the fourth line, A comma B equals B comma A. So this is what is, I'm gonna look up the ChatGPT that I did earlier this morning, because I don't want to mix words. Oh, wait, hold on. It's probably in here. So they called it, yeah, Python's tuple unpacking trick. So it basically swaps A and B, and I didn't know that. Yeah. So that's pretty cool. Yeah.
So it wants to put basically if A is less than B, we want to put the larger number first.
Yes.
So we want to make sure that we're in descending order, basically.
Mm-hmm. Yep.
Okay, that's fine. So make sure that these two numbers are in descending order is the first line.
Yep.
Then subtract them so you end up with a positive number.
Yep. And then when it hits 0, then the remainder is essentially the GCD. which is
Hold
going to
up.
be A.
If you're in descending order, A minus B will be a negative number?
It's no, it will be a positive number because it's going to reorient A and B. What you should do is use your tablet and then do a full screen on walking through this code, handwritten, with the print GCD 36 and 14. Then you'll understand.
Okay. Then let's do that. Boop.
Yeah, I was doing this on the treadmill. I was like, oh, okay.
Let's do that. Let's see. Share my screen. Yeah, share like multiple windows. Blow this up. All right, so let's see. Probably need both then.
Yeah. I mean, you could just copy. You can copy paste into Miro. Just grab the code and then paste it in there, and then just work
Okay, this works here.
the second print statement.
So we have definition. So given A and B, I'm going to write it out. If A is less than or equal to B, swap A and B, return A if B is equal to 0, else GCD, it's recursive, B, A minus B. Okay, let's do an example of this. So given A equals 36.
Yep.
And B equals 14. So A is less than A and B. Don't need to do that. So don't need to swap.
Yep.
And we'll return. B is not 0. So we're going to do the same thing.
Yep.
We'll do GCD of 14 and 36 minus 14, which is equal to 12, which is
22.
going to be what?
22.
36 minus 14 is equal to 22. Lol. Which is going to be, so A is now less than B. So we swap them. So now,
Just do it vertical so you don't have to pan around so much.
Yeah, that's fine. Just trying to think. I'll get used to doing this on the whiteboard. I've worked on whiteboard a long time. So now this is equal to, let's do the swap here. Swap AB. A is now equal to 22. B is equal to 14. And then B is not 0. GCD of, is it A or B of 14. And A minus B. So 22 minus 14 is equal to 8. Once again, so we'll do a swap. A is equal to 8. B is equal to 14. No? That's not right. Don't need a swap.
You don't need to swap, yeah.
That's going to give us, so B is not equal to 0. So we'll do GCD of A 14 and 8. 8 and 14 minus 8 is equal to 6.
Yep.
This just keeps on going, huh?
Yep. Well, only for a few more lines. Or
Yeah.
maybe,
So
maybe
now
a
we're
couple.
going to do same thing. GCD, because they're in descending order again. 6 and 2. GCD of 2 and 4. GCD of 2 and 2. And GCD of 2 and 0. So 2.
There you go. Yep.
Interesting.
Yeah.
They work with odd numbers. I'll try that. That's cool. I've never seen that before. No, it's an interesting way of doing a nice, short, like concise way of representing a function that does that.
It gets better.
Wait, there's
It gets
more.
better. Yeah, hold on. If I hit the power, yeah, okay. Watch. So, however, such an approach in the worst case scenario still requires linear time and the size of the numbers. For example, when computing GCD of n in 1, the following lemma will be extensively employed in the so-called Euclidean algorithm, which will reduce the complexity down to logarithmic time. This is where it gets cool. Corollary 3.8 for any a or b that exists within the integer set z. We have GCD of A and B is equal to GCD of B and A mod B. Now this is much better. Let us apply this idea again, but with the modulo operations of subtraction. And then this Python code, def GCD, and then it declares, it's just typesetting A and B as ints, output typeset as int, return GCD B and A mod B if B is not equal to 0, else A, and then it's got a few different print statements for running through that GCD function's output. But yeah, this is even more, it's like now it's one line, and it's pretty what do you call it?
Concise.
No, there's it's like when you get like it's like ASMR for your brain when it like, yeah, it's
Efficient?
concise, but like it's concise and efficient, but like it's called something. This is like a word that mathematician, yeah, it's like that, getting closer. It's like in that ballpark. Yeah, it's math sexy, but like anyway. Notice that if I remember it, I'll bring it back up. Notice that the algorithm can be easily implemented in a single line. Moreover, the complexity reduced down to logarithmic time. No. But I laud your attempts. For computing GCD A and B, we need O of log max AB time. Example 3.4, let us find the GCD of 535 and 230 manually. We will use the Euclidean algorithm for this purpose. 535 equals 2 times 30 plus 75. So this follows the same structure as was given like in one of the previous, I think, lemmas, where it's just it's A is equal to QB plus R, and it's just doing the same format for the subsequent two lines. So 230 equals 3 times 75 plus 5. 75 equals 15 times 5 plus 0. So once you have a remainder 0, you know that your B is 5. Yeah. Because it's the B, because it's A is equal to QB plus R. So GCD is 5. While the greatest common divisor GCD focuses on finding the largest shared factor between two numbers, the least common multiple LCM deals with finding the smallest multiple that both numbers have in common. The LCM is particularly useful when we need to synchronize cycles or work with fractions. So this is what I was telling you before. Like, I don't know what synchronized cycles means. I'm sure we'll understand that later. I
imagine we'll get to that later. That's like kind of like a foreshadowing.
Yeah, exactly. Okay, definition 3.5 or 3.9 LCM for any A or B that exists within an integer set Z, the least common multiple LCM A and B is defined as an integer M exists within the natural set of numbers N such that 1, A is a divisor of M and B is a divisor of M. 2, B is a minimal integer that satisfies the first condition. One might write the above definition more concisely. Least common multiple of A and B is equal to the minimum of M that exists within a natural set of numbers N. I don't remember how you read the colon. How do you read the colon?
Divisor
Such
of.
that? No, colon, not a bar. This one
Parameterized
here.
by.
Parameterized by. A is divisor of M and B is a divisor of M. Example 3.5. Let us again find, but now least common multiple for few pairs of numbers. 1, LCM of 12 and 4 is 12. 2, LCM of 13 and 17 is 221. 3, LCM of 13 and 18 is 234. 4, LCM of 42 and 28 is 84. Let's scroll on this. Lemma 3.10, least common multiple properties. We consider LCM of A and 0 to be undefined. LCM of A and B is equal to... do we know how to read this? Did you chat GPT this one?
Where you at? You're not scrolling. I'm doing. Where are you?
I am on lemma 3.10, second item, and it's essentially like the same as.
It's like interchangeable with, like.
Yeah, that's how I read it. But like, okay, I'll just say it like
it's
that.
The same as. Like, I'll look it up.
That's how I read it, like the same as, because it's just keep it simple.
I'll look it up while you do that.
All right, least common multiple of A and B is equal to A, which is the same as B is a divisor of A. If A and B are co-prime, then least common multiple of A and B is equal to A times B. Any common divisor delta of A and B satisfies delta is a divisor of least common multiple of A and B.
If and only if.
If and only if. Wait, really?
It says the least common, like according to Claude Haiku 4.5, the least common multiple of A and B equals A if and only if B divides A.
Oh, okay. I didn't know that. That does. Why don't they just put the IFF? Because that's how I usually see if and only if written.
Me
Why
too.
do they have two symbols?
It's fucking
whatever.
math.
That's part of why this is complicated for people, is because you have to like learn the jargon, because white papers, like cryptography white papers, there is no unifying symbol set, so you have to know all the different, like, essentially synonyms of a given symbol and how they can be parsed. But anyway, problems down the road. Or for any C is greater than 0, we have LCM of A times C and C times B is equal to C times least common multiple, or LCM of A and B. Integer is LCM A and B divided by A, and LCM A and B divided by B are coprime.
Oh, okay.
These are really important constraints, and I'm sure that there's like really
it's like optimizing circuits. This becomes like really important information, right? This is like
right.
It's like because you want to optimize a circuit, you want to try and find the least amount of operations required to complete the circuit.
Yeah,
and you can use a lot of these tricks in order to make it minimal, because you can start to do, like, you can do the algebra on all these things and say, because this and this, we can then rearrange things, and then we have this thing which equals this thing, and now it's like two operations, right?
Yep. Because at the end of the day is like, if you can reduce the operations, you increase the speed, and time is money.
Yeah.
So theorem 3.11 for any A or is it A or B? For any A or B belonging to a set of natural
A and B in the natural numbers.
For any A and B belonging to the set of natural numbers N, we have GCD of A and B times LCM of A and B is equal to AB. One interpretation of the above theorem is that no additional algorithm is required for LCM of A and B if we already have an algorithm for GCD of A and B. Indeed, we can simply use the formula LCM of A and B is equal to AB divided by GCD of A and B with the previously computed GCD A and B. Excuse me. The reasonable question is how to generalize the GCD and LCM operations to more than two arguments. For that reason, we provide the following definition. Definition 3.12, GCD and LCM for multiple arguments. We define the greatest common divisor GCD of a sub 1 to a sub n, and the least common multiple LCM of a sub 1 to a sub n for any set of integers a sub 1 to a sub n that exists within the integer set Z as follows: GCD of a sub 1 to a sub n is equal to max of D exists within the natural number set n, parameterized by D as a divisor of a1, a sub 1, D is a divisor of a sub 2, and onto D is a divisor of a sub n. LCM of a sub 1 to a sub n is equal to the minimum of m that exists within the natural set n, parameterized by a sub 1 is a divisor of m, a sub 2 is a divisor of m up until a sub n is a divisor of m. Theorem 3.13, computational properties of GCD and LCM for multiple arguments. The following two statements are true. There exists for all A and B that exists within the natural set N, is parameterized by GCD of A, B, C is equal to GCD of A and B and C. I guess that if you're hearing that, it's hard to visualize that because technically there's a parentheses within the parentheses because you're doing a GCD operation on A and B.
Yeah, you have to like read them inside out, kind of.
Yeah. So the output of the GCD of A and B is the first parameter of the second GCD.
They're commutative as well. So it's like transitive and commutative.
Yeah.
You can apply the operations kind of like at will and move them around, which is nice.
Yeah.
Hold on. There's no C in that last one.
Yeah, I just saw that.
How'd they get rid of the C?
Maybe because it's a common factor for both, so you can just remove it, and you just need to find
some constant.
But it doesn't. Hold on.
It's factored out
because this is natural number set. Yeah, it does factor out.
But it doesn't say what the C is. It just says constant. It's a factored out constant.
Right. It doesn't
specify. Says what and B are natural numbers. C is any constant, apparently.
Would C be what would C be? Would C also be potentially a natural number?
I need an example.
Like if you have,
it could be, but apparently it doesn't need to be. Or I mean, so it could be anything as long as you can factor it out.
I think this will make more. I like it. We're making guesses.
Yeah.
But it would be nice to just see the worked example. But that makes sense that C somehow
one here
factors out. I'm sure there's one of you. Nope, there's no. There's probably one at the end. We can ask ChatGPT for one. In conclusion, from these two theorems, there is no conceptual necessity for specific algorithms for GCD of anything and LCM of anything when dealing with more than two arguments. It is worth noting that there are more effective algorithms for more than two arguments, but such a topic is well beyond the scope of this book. Interesting. I can read this, or you want to go?
I'll go.
All right. Extended
Euclidean algorithm. So, in this section, we will introduce the extended Euclidean algorithm, an important lemma related to the GCD. So, greatest common denominator. You might have reasonable question. You might have a reasonable question. You might have reasonably questioned. Oddly worded. Why do we even need an extended version? One of the primary reasons is that this algorithm will help in finding inverse modular elements introduced in the subsequent sections. Inverse modular elements. Interesting. Lemma 314, the Bezout identity for any two given integers, A and B.
I had to look that up.
Bezout?
Yeah, it's French.
Sure. I'm American.
Sure.
I'm American. Bezout.
Bezout.
The Bezout. And for any given two integers, A and B, that exist within the natural numbers, with D equals to the greatest common denominator of A and B, there's just such a U and V that exists within the integers such that D is equal to A of U plus B times V. Interesting. So let's see here. Example. It is evident that the greatest common denominator of 125 and 93 is 1. So we can find such U of V exists within the integers that 1 is equal to 125 times U plus 193 times V. One such example is u with the 32 and v with 43 since
Mm.
that.
It's so nice to see a worked example.
We call the tuple 32 negative 43 as the Bezout coefficients.
Yeah, like that makes sense. Interesting.
We'll explain and show how to find these coefficients concretely a bit later. What are the purposes of coefficients?
Now, how many of those exist? I wonder if there's another.
I'm also curious as to like what are the benefits of knowing these things? Like, why would we care, right? Because like previously, if you've watched this whole thing, like you can see some of the benefits of knowing. Maybe you haven't yet. You will probably get to the point of understanding why we need to, like, in math, right? There, I was like, why should we care about this? And it's always because it's useful for doing something. And a lot of the stuff we've learned so far, we'll learn later that it's useful for optimizing circuits, right? Doing algebra to get to a point where you have the minimum number of operations within the circuit to then provide a proof, which makes it more efficient, and you can require less resources to get it done, et cetera, et cetera. I'm assuming this is also useful for that, but I have like no intuition as to why or how. See, corollary. From the Bezout identity, integers u and v are of different signs, excluding the case when either of Bezout coefficients is 0. Okay, interesting. Generalization for multiple integers. Suppose d is the greatest common denominator of a through n. A of 1 sub a of 1 to a of 2, all the way to a of n. Then there exist such integers u of 1 to u of n that exist within the integers that d is the summation from I to n of ui ai. Okay, so they're linear combinations of each other. That's interesting.
Yeah.
That's going to be useful for polynomials, I imagine.
Yeah. It looks like it could be.
The integers u and v are called Bezout coefficients. The first corollary can be understood intuitively. If all coefficients are non-negative, the result will be much larger than necessary. Similarly, if they are non-positive, the result must be negative, but the greatest common denominator was defined to be positive. The second consequence follows from the fact that we can decompose the greatest common denominator, thus sequentially derive this sequence. Also note that we can find Bezout coefficients in each Euclidean algorithm step. I would be curious to see the like a geometric representation of this. You know how like if you were to watch like 3 brown 1 blue or 3 blue 1 brown.
Yeah. The animations of
he does a lot of really
space.
good visualizations of these types of things. I bet there's like
Does
a
he
really
still
good
work
one.
alone?
Does he work alone? I think so.
Yeah.
I mean, he's done a lot of collaborations lately as he's gotten bigger, but like for the most part, I think
the animations of the n-dimensional space, because like Veritasium, that one, like
people started using. So he built that whole library called Manum, which is a mathematics visualization tool. You know, it'd be interesting if we tried to use like ChatGPT or AI or Claude to like do a Manum visualization of these things.
We could do that.
That could be fun.
That would be awesome. Yeah.
Unless someone in the audience who watches this wants to do that.
No, there's zero.
I know one person's watching and I'm talking to her. So you can go do that.
Oh, there's somebody watching?
Yeah. Maya's watching.
Oh, okay. Hi, Maya.
D has entered the room. Hey, let's get rid of your second screen because we're watching mine.
Okay, hold on. Let me get rid of it.
What's up, bro? Audio only. Anyway, D can listen. Let's see. Now we introduce the extended Euclidean algorithm, which is besides calculating the greatest common denominator itself, finds the Bezout coefficients efficiently in the polylogarithmic time. For example, as we will see, for calculating the modular inverse element, one would rather use the extended Euclidean algorithm than the naive approach, which shows whether inverse exists at all. The time complexity of the extended Euclidean algorithm is O of log max A and B minus the same as for the classic Okay, so it's the same. So it's the extended algorithm is the same order of polynomial time complexity. What is this QR code you're putting up?
That's not me.
D's doing something. Discord? What is this? Say something, bro.
That would actually be useful.
Yeah, we should. Can you stream to Discord? And then we just take. We could like funnel people to the Discord who want to like participate in this.
Yeah.
Or something. I don't know.
I could share screen to Discord through OBS. That has to be so I can run slobs on my end and then screen share that into a Discord channel that we are both in. Yeah. This is a lot. We're streaming to a lot of places at that point.
Fuck it. Whatever. Who cares? Maybe somebody's learning some math.
Saying.
If one person learns some math, then it's fine because I'm learning. This is a fun way to treat my Saturday.
I'm going to be honest. I don't care about anybody else.
No, I'm having fun like learning this stuff myself.
Yeah.
I hope we get like balls deep into it. And someone's like, I learned ZK through watching you guys.
That would be funny. Be like, wow.
You must be really bad at ZK.
No, they just like sometimes it's better to have company because learning something that's really this boring, it's painful if you just do it alone. Yeah, I've done that before.
Yeah, I'd be cool to have. Like, we got some comments, by the way. Coming up here. Let's see. Cheat viewers, Streambo. That's garbage. Join the Discord. D's got Discord stuff. I think what he put up is the Discord.
Oh, okay.
Okay, that makes sense. D is typing for us. He just said, "Ignore me. I can't hear you." In my bro. Okay. D is producing while we do content.
Okay, algorithm 1, extended Euclidean algorithm. Input A and B, parameterized by A and B, exists with a natural set of numbers n without loss of generality. A is greater than or equal to B. Output GCD of A and B is the first input. U and V are the second and third inputs. R sub 0. So A is going to R sub 0. B is going to R sub 1. 1 is going to U sub 0. And 0 is going to U sub 1. 0 is going to V sub 0. 1 is going to V sub 1. While R sub I plus 1 is not equal to 0, I is equal to 1 to 2. This is what do you call it? Pseudocode. So like instead of somebody actually writing the code, they're just writing essentially functionally how I'm going to keep calling it business logic, but essentially how the function should be written. So this is as close as you can get to like human readable code, I suppose. You can probably you can get
pseudocode is like pseudocode is useful for implementing something in any language. Usually, that's why people like using Python, because Python is very like the syntax of writing Python is very close to writing pseudocode.
Yeah,
and so people usually when they do like specifications, which are supposed to be as close to implementation generic code, they write it in Python because it's close to pseudocode more often than not.
Yep. There's also languages like that are newer, like Zigbee, which I haven't taken a look at, but I heard that.
And like Quint is a specification language. That's something that got put on my radar the other day when I was talking about specs. It's made by the team that did Cosmos and what's their consensus algorithm off the top of my head?
Oh, no, I'm not going to remember that one.
Why have I forgotten that? Doesn't matter. Anyway, it's very BFT, right? And so I think PBFT, but they made a.
I can look it up. Tendermint, yeah.
Tendermint, yeah. Ethan,
yeah.
Created Quint in order to help verify a bunch of to-dos like executable specifications and writing specs. Mm-hmm. He says it's nice. I haven't tried it out yet. I'm thinking about giving it a go on like taking one of our specs and writing it in Quint and seeing what that process is.
Interesting. I mean, specs are already pretty like the way that IETF pushes out specs. They're pretty readable, or like the EF.
It depends though, right? Because I've been diving into a bit of a tangent. I've been diving into the difference between the Ethereum Foundation process of what it is today, which is executable specs, and the EIP process. So like EIPs are like the process for changing specs and introducing new things, whereas the final
you should
document,
say what it is for people who don't know. Ethereum Improvement Proposal. That's how you submit changes.
Yeah, and then what that then generates is like this canonical document, at least when it comes to like code, of an executable specification, meaning that becomes like the reference implementation for how you write the software in any language. And so that then allows you to do a lot of automation, like generating tests and frameworks and stuff like that. And then someone's like, I'm going to write this in Go or Rust or Nim or whatever, like C or whatever, or fucking
it's
Swift.
agnostic to the
Like Bean.
language.
It's agnostic. And so
Yeah.
they should all, if you do a function, if you write a function like this, it should give you the same answer every time. So,
And if it doesn't,
then
fucked up.
that's problems.
All
All right.
That's why like shout out Mammy writing Constantine, which is a cryptographic primitives library in Nim. Like that's all. It's been something everybody's been impressed. Yeah,
pretty hardcore. Name is great.
Yeah, it's pretty hard. There's a cool repo I'll share with you later in terms of how to build everything from scratch. Anything you want. It's pretty interesting.
What, Constantine?
No. I'll show you later. But anyway,
Okay.
we'll finish up this page because it bleeds into a new.
Yeah, it gives us
section,
10.
and
This page
almost
is
an hour.
10. So we'll just finish, go up to prime numbers and we'll start there next time.
Yep.
Okay. Go ahead.
So although we already know how the extended Euclidean algorithm works, this method is still not very intuitive. Let us consider an example to better understand how it works. Example 3.7, extended Euclidean algorithm example. First, we need to, okay, I'm gonna have to correct some more typos. First, you need to find D is equal to GCD of A and B. Then knowing the sequence of expansions, quotient Q sub I at each step, we can find the Bezier coefficients. 125 is equal to 93 times 1 plus 32. 93 is equal to 32 times 2 plus 29. 32 is equal to 29 times 1 plus 3. 29 is equal to 3 times 9 plus 2. 3 is equal to 2 times 1 plus 1. 2 is equal to 1 times 2 plus 0. Let's see what is going on this table here. So you have I0.
The dividers are the first row. Those are the Q's, the quotients.
Yep.
1, 2, 1.
This is the iteration step, by the way. So
these...
zeroth 1, 2, 3, 4, 5, 6 right here.
And then what the fuck?
So it's just tracking. So like this is Q. So Q is 1, 2, 1, 9, 1, 2. Yeah, that matches. And then U is an invisible 1. And then because it's what is the U is next to Q. So 1. Why is this 0?
So what are we getting here?
It's asking you to do 5 and 6 so you can calculate V sub I. It's an example in this table. Here, each corresponding cell is calculated with the following formula. So they're giving you the formulas so you can calculate V sub I of I is equal, where I is equal to 5 and 6, so you can fill out the rest of this table. But essentially, they're showing you how the table is populated based on the iterations of this example. 125 is equal to 93 times 1 plus 32, all the way down to when you have a remainder 0.
Yeah.
We should spend a bit of time outside of this recording and then just work through some of this because this is still a little bit not so intuitive for me. So I'm going to do this one. I never got to this. But yeah. So exercise, finish this example by filling in the missed cells marked by the question mark. After finding V sub 6, be sure to check yourself. So this is something that we could code and then just, verify, like do it by hand, then write the code, and then just you can post the Python code in the Discord server or the comments section in the YouTube or wherever.
Yeah.
Cool.
Sweet.
Well, that is it for this weekend's next 10 pages of the ZK book. I hope you tune in for next time where it will get even more mathy. Yes.
While my kid takes a nap, we will do ZK or primitives of ZK.
Can't wait till we actually get to write Circom stuff.
That is gonna be neat. Yeah, it's gonna be fun.
All right. See you guys and end the stream.
Later.